Very good. All right. Well, thanks for having me. Again, I'm Matthew Shupe, University of Colorado in NOAA in Boulder. And here we'll talk about MOSAiC. I'm going to provide a little overview looking at the challenges of this year in the Arctic and really the opportunities as well. And I kind of view the challenges as opportunities, as you'll see through the presentation here. Just to start off a bit about motivations. Why did we do MOSAiC? And I'll get a little more into what MOSAiC is in the following slides. But the motivations, of course, I think most people on here probably know if you're on this call. The Arctic's changing very rapidly. The sea ice is in decline. There's amplification of temperature changes in the Arctic. Our models struggle to represent a lot of these processes, these changes. And of course, there's a lot of emerging operational and management needs in the Arctic as the Arctic is opening for business, for resource development, and furthermore. And then, of course, there's a lot of questions about the connection between this changing Arctic and the rest of the global system in terms of things like weather forecasting and how that affects lower latitudes. And we all know there's a dearth of observations in the Arctic. So these things kind of provided some foundational motivation for wanting to go into the Arctic. And so over the past, I've put 12 years into this so far, and we've had a whole collection of people internationally that have been planning this for, this decade kind of scale for this expedition into the Arctic. And this really started a lot of the planning initially through the International Arctic Science Committee. Of course, the Alfred Wegener Institute played a really important role as the lead institution, and many US agencies have been involved for a long time. The expedition at its nature is an atmosphere ice ocean expedition where we really cut across the Arctic system looking at the physical, chemical, and biological processes. We really designed this to have this kind of multi-scale approach with kind of point measurements at our primary facility, which is the Polarstern icebreaker embedded in the sea ice, a grid scale, kind of grid cell observations spatially. Ben will talk about that some with the distributed network. And then we really wanted to put this in a pan-Arctic scale to look at how the kind of MOSAiC kind of central activities relate to the rest of the Arctic. This has been an integration of observations and models from the very beginning. We have key people from both communities working together to design this project and to really implement it. And of course, the annual cycle is such an important part of MOSAiC, getting the full year to understand how processes are interacting across these different seasonal timescales. So that's kind of some of the context and the plans that went into the expedition. So how did it go? The Polarstern is almost back home to Germany. It'll be here in a couple of days. How did this whole year in the Arctic go? And I'll just tell you right away, it was a series of challenges and also opportunities. So let's take a little bit of a journey, and I'll have a lot of photos here to kind of take you along that path. I'll also use this map on a few occasions. This is looking down on the Arctic, and the different colors will show different parts of the MOSAiC expedition, different legs, if you will. This is for leg 1. The red little squiggle there is where leg 1 occurred. You see some dates there. You also see the ice edge from the middle of September. This is the sea ice minimum, and the sea ice maximum from March are both included on this plot for context as well. So with leg 1, it started back in last September through the middle of December. This was a time when we installed a lot of equipment on the ship. We installed the ice camp in the ice, the distributed network that Ben will talk about. We started physical sampling. We found ice that was thinner than expected and very dynamic. And so I'll get into some of those concepts as we go forward here. Starting in Tromsø, Norway, the ship was packed with all kinds of great science equipment. Here's a scanning cloud radar from the DOE program going on board. This is the first time a system like that's been operated in the Central Arctic. So much science loaded on Polarstern, just packed full of equipment to go into the Arctic. And then, of course, we sailed out into the ice pack, trying to find a floe to moor to. And turned out the ice was thinner than expected. And of course, we all expected thin ice, right? We know the ice is thin, but it was actually thinner than we expected. And that posed us a first challenge for us to find a flow that would be suitable. And we had to kind of settle, if you will, for a little thinner ice flow than we had hoped for. Of course, we got out and explored flows, looking for how thick the ice is and kind of putting out in our minds what the map might be, how we could install our different equipment out on the ice. And then started installing our ice camp. So here are some pictures of the early installation time period, sticking equipment out on the ice. Here's a picture as the dark descended on MOSAiC out at Met City. So these are some installations out on one of our kind of cities out on the ice, about 500 meters away from the ship. A bunch of installations there. Here's a nice picture installing a sediment trap, kind of a little buoy to catch some of the sediment falling below the ice. So many different installations out on the ice. We also started a comprehensive measurement and sampling program to look at everything you can imagine, right? Here's a person looking at the snow. Of course, we collected snow samples, ice cores, water samples, air samples, all kinds of samples to really document and explore the different components of the coupled Arctic system. And the dynamics. Yes, the ice was very dynamic from the very beginning and through the whole year. This is a picture looking off the ship right into our logistics area. You can see the gangway leaving the ship. Already in our leg one, we had a big crack going right through the middle of that. Here's another picture looking out towards our camp. That's Ocean City, right out there in the middle of the spotlight. You see a big lead forming off behind there, and Met City is on the other side of that lead, so cut off already from some of our assets. Here's where some of the ice came together, forming a ridge that crunched over some of our power lines and other things. So you can see right away, right as we got out there, it was already a very challenging situation, and we had to, it turns out, reinstall and move a lot of equipment around many times over the course of the year. So let's move into leg 2. This is in the yellow here. This is the heart of winter. This is darkness. This is no sunlight the whole time until I think leg 2 people, Ben was one of them, he might tell you about it. The sun was barely coming out at the very end. This was a little bit of a kind of less dynamics at the time, less ice breakup, so it helped for a little more consistent operations, perhaps some of the most consistent of the whole year. It was very cold and dark, temperatures down to -43°C. And one of the great questions for the wintertime is what's happening to the biology in the middle of winter with no sunlight? I don't have a ton of pictures, and maybe Ben will have more, I'm not sure. A couple great pictures though. Here's a picture from one of the leg 2 participants showing a flux station for measuring surface energy fluxes out there under the starry night. Just a really beautiful scene. Really struck me for leg 2. Another great picture of some biology, some copepods here. This is actually one of the great questions, and I don't know the answer right now for what does happen to the biology in the middle of winter, but you know, we have some fantastic data to really get after that question. And I know there's teams of people that are looking at the different aspects of the ecosystem and biogeochemistry that's happening in the wintertime, so we can really get a handle on some of those processes. Now we come to leg 3, and leg 3 was quite an adventure for those fortunate enough to be out there on leg 3. Maybe some wouldn't agree that it was fortunate. This was an extended leg, extended in part because of the coronavirus and challenges to rotate our people. This was a leg from early March through early June, and it was characterized by very rapid movements of the ship that was installed out there and all of our drifting assets. You can see this very long green line. And I'll talk a little bit in a couple slides about the large scale circulation that led to that with very high Arctic oscillation indices. So rapid drift, lots of ice movement, lots of ice dynamics. Yet again, we'll see a little bit of that. And also some nice events, some warm air advection events that proved to be really interesting for this leg. So to touch first on the Arctic Oscillation Index, this is about the last 8 years of the kind of monthly values of the Arctic Oscillation Index. And I'm not going to go into the details so much of this, but this basically quantifies the large scale circulation. What do the patterns of the circulation look like in the Arctic? And the point here is that in early 2020 here, for a number of months, the value here of the Arctic Oscillation Index was very high. It was actually historically high for quite a few months. And so what this means is conveyed in this next figure, which is a composite analysis of wind speed anomalies relative to climatology. So the colored areas say, hey, there was extra winds at these times. And this is for the months of January through March of 2020. And here's Greenland, and we have Svalbard. And so the ship was not too far from the North Pole during this time and drifting towards Svalbard, right here in this band of anomalously strong winds that are kind of pointing to the south. And so these anomalously strong winds, they were really stagnant, and they just blew the ice and the ship with it along this transpolar drift, faster than we anticipated. So that again was a little bit of a challenge. Another really interesting thing about leg 3 is embedded in this figure. This is a figure of temperature profiles from the seasonal ice mass balance buoy that was operated by Don Perovich out as part of our network there. And what's showing is temperature. The very top is the atmospheric temperatures. The surface is somewhere around 0 here. It kind of moves up and down based on the evolution of the surface height. And down in these negative depths are down into the sea ice and ocean. And you can actually see here these kind of black contours kind of show you about the ice growth over the course of the year. That's about the ice bottom and the ocean down below that. And you can just see temperatures throughout the ice here. So now as we get towards the end of winter time, there was actually this really interesting event in middle of April. It was a warm air advection event, warm air coming from the south up out over the ice pack. And this is really interesting for many of us that study atmospheric drivers of the system. And this warm air event actually really brought warm air aloft, but it really pumped a lot of warmth into the sea ice. And this is kind of where this progression towards the summer melt season really started. You know, the melt didn't really set in for quite some time after that, but this is a really important event to really kick the system in a certain way. And this event actually is one that is a focus for the WMO Polar Prediction Project right now. This is the YARP, the Year of Polar Prediction, is going on, and it's a bunch of international models coming together to study the Arctic system. And so MOSAiC and YARP and PPP have teamed up to study this event and evaluate how models are representing these important kinds of events. Of course, on leg 3, there were also dynamics. MOSAiC was sitting right in a major ice shear zone. And so you can see in this picture all kinds of ridges and leads around the area. Again, leads are cutting off Met City. That was my home for most of this expedition, and boy, it was moving all around. Really having a hard time accessing Met City. Moving on to leg 4. So the transition between leg 3 and 4 was actually really interesting, and it was delayed by about 2 months due to the coronavirus. And so, you know, those people that were out on leg 3 had a little longer stay in the Arctic than initially planned because of the challenges with travel in the era of coronavirus. But we actually had to bring the ship out of the ice in order to facilitate this rotation. So that was a little bit of a bummer because it interrupted some of the time series, but we actually had a lot of instrumentation that was autonomously operating in the ice to capture the processes happening during this time period, during this exchange. So moving into leg 4, then we had a little bit of this interrupted start due to bringing the ship out and taking it back in. There was a little bit less cracking of the ice because a lot of the ice was in free drift at this time. The individual ice floes had melted out enough, so they were kind of uniquely flows now, and they less stress across the ice. It was really a fantastic melt season. We followed the melt season for the MOSAiC flow all the way until the edge. As I said before, the ice flow had drifted further than we thought it was going to drift, and so we actually drifted all the way to the ice edge, and this flow basically totally disintegrated at the ice edge, and we measured it the whole way. So that provided this opportunity to really measure rapid melt, a lot of freshwater formation, and the processes involved in that. One point I want to make is that fortunately we had tons of instrumentation on board the ship. So even though the ship had to move for a while, we actually had lots of great time series, especially of atmospheric measurements. You see all these containers up front and lots of equipment up on the top of the ship. These are all making continuous measurements even as the ship kind of left the ice and came back. So it actually is kind of a bonus data set of some spatial context for a lot of the types of measurements that we've been making. This is a picture of the flow as we returned back to the flow, looking at it from above. This is a remnant piece of the original flow. Little parts had broken off, but you can still see a pretty big area of flow, about 1 kilometer across. And you can see melt is starting. It has some nice melt ponds on the flow. This is a very cool image. This is a laser scan taken from a helicopter to map the flow. And I'm going to put the boundaries on there to help you. The white parts are ridges, the dark parts are melt ponds, so you can see a lot of texture of this flow. And just to show you the sheer magnitude of science, the activities that we had going on, this is what our map looked like of our different sampling areas, our installations on the ice, our pathways, and what have you. You see the ship here at the bottom and all kinds of equipment out there. We really did tons of science on this ice flow, just packed it in there. with so much great science. You can imagine that the melting posed a challenge for a lot of our installations, so we built bridges and we found other unique ways to get around. Of course, all kinds of great sampling with ice coring activities. We did lots of transects around the ice flow to understand ice thickness, melt pond depth, snow depth, all kinds of different parameters as they evolved in time, including things like optical parameters at the surface. What is the reflectivity of this melting ice surface? Here's some folks making measurements in the ocean. This is a really interesting time in the ocean because a lot of this meltwater was pouring in, leaving this fresh layer near the top of the ocean that was actually sitting on top of the salty ocean below, and it served as this kind of interesting interface where the biology occurred, and that fresh water layer actually kind of prevented a lot of mixing of heat upwards and gases upwards and things like that. So it was a really interesting component of the system that we spent a lot of time focusing on. So as I said, the end of leg 4 actually ended in a bang. The ice flow totally fell apart. The day after we decided, hey, it's getting a little bit sketchy here, let's bring our stuff back on board, the whole thing just fell apart into 1,000 pieces. It was a really amazing timing right near the ice edge. So we measured all the way up to the very demise of that ice flow and then turned over the keys of the ship to the next leg, leg 5. And those people then took the ship back to the north. We wanted to go back and embed in the ice to capture the rest of the year. They went up past the North Pole and installed up here in this little purple area to drift for the last month to really capture the sea ice minimum time and to capture the freeze onset. These are really important times of the year to really bring this expedition full circle. I don't have a ton of pictures from leg 5 there. Those people are still coming home. Here's a couple though. The third installation of the MOSAiC flow used helicopters. You can see some radiation equipment down there on the ground. They're moving things around here to set it up. And freeze onset was a really important thing to capture, right? We're interested in the processes related to when the ice starts to freeze again. So here's an installation going right on top of a melt pond, just as it's starting to freeze up, to really capture the energy transfer related to that process. So some fantastic measurements. I'm really excited to see what those look like as we get those back home. And just for some context, this is the annual cycle of the sea ice extent from the NSIDC. And for our year here, the 2020 year, it's the blue curve, and we see that, wow, the ice was very, retreated quite a bit this year, but didn't quite make a record. You can see the record was from the year 2012. So we had a very low sea ice year, but this is actually the second lowest year ever, not the very lowest. So again, just a very interesting year to be out there, to be right in the middle of this rapid decline of sea ice, this rapid movement of sea ice. So it was really an opportune time for MOSAiC to be there. I want to touch briefly on modeling activities. There was lots of modeling activities going on, and there are more planned, of course, in the future. One was led by some folks at NOAA, which is some near real-time verification using data from the field to evaluate some operational and quasi-operational models, to look at the processes in those models and to understand biases. Another activity is the development of merged observatory data files. This is taking the data, the observations, and packaging them in a way that are really ready for model evaluation. This is in partnership again with the WMO Polar Prediction Project and the Year of Polar Prediction, where these data sets will be used in conjunction with data sets coming out of models to evaluate again these operational models and how they're doing with representing the Arctic system and the various processes related to the sea ice and others. And there are 70+ discrete modeling activities that are part of the MOSAiC plan. So all kinds of modeling going on and planned for the future here. Wanted to touch also on outreach. MOSAiC, of course, is so photogenic. It's a really fantastic opportunity to bring the general public into the Arctic, to show the importance of the Arctic. And there's so many things that have happened related to MOSAiC and outreach. The background picture here is an extract from a planetarium show that was produced by Amy Richmond called Into the Polar Night. So you can imagine being embedded in a planetarium and being there out at MOSAiC. So there's this show, there's another one that's being made right now. So look for those in your local planetaria, hopefully, and you can find them online in YouTube. There's also documentaries being filmed, a couple of those. There's all kinds of curriculum development, K-12 outreach, teacher engagement, workshops. There was a development of a massive open online course where many MOSAiC PIs and investigators provided lectures that are now in an online format and have had more than 2,300 learners using that resource. And of course, tons of media engagement throughout the year and continuing. So by the numbers, MOSAiC had 20 nations involved at a funding level and much more as far as the nationalities of the participants. 7 icebreakers or ships involved, 60 institutions or more than 60 institutions, and more than 400 field participants. That's pretty amazing when you think about the Central Arctic. Total budget over $150 million and more than 40 million from the US. So in summary, MOSAiC has been many challenges. And apart from COVID and the coronavirus pandemic, a lot of these challenges, however, can be viewed as opportunities. It was really our opportunity to be embedded in the middle of a very dynamic and kind of emerging ice pack. So we were right there to experience the Arctic as it revealed itself to us. And there was so much science. We packed science on the ice, on the ship. Everything you can imagine was measured. And I think this is going to be a tremendous data set to look at so many different processes. There was very broad participation, internationally, interagency, interdisciplinary. It was really magical to be there and see all the coordination, the collaboration, people supporting each other, all for a shared mission. And capacity building. We've built this whole new generation of trained Arctic field scientists, and we've developed new concepts for how to do research in thin ice. So this will really serve the community in the future. And what would it be without a picture of a polar bear? Okay, we had lots of polar bears as well, cute polar bears just like these ones, actually really amazing experiences. And fortunately, both humans and polar bears were very well behaved, and we collaborated well out there on the ice pack. So with that, I'd like to close with thanking our US funding partners, NSF, DOE, NOAA, NASA, and of course, Avi contributed so much to the funding of this whole activity. I really want to encourage these funding agencies to continue supporting MOSAiC. We've collected a great data set, but there's so much analysis to do. So I would say the research is just beginning now, and we definitely need to continue to invest in the future of MOSAiC to really get the most out of that. And I'll point you to a couple of web pages at the bottom there. And with that, I'll just say thank you.
Thank you so much, Matthew, for your presentation. We will now turn it over to BenRabe. Ben, go ahead.
Yeah, good evening, good morning, good midday, wherever you are. It's actually evening here in Germany. Yeah, I am BenRabe, and I'm actually working at Alfred Wegener Institute, and I was already introduced by Liz. So without further ado, I'm going to tell you a bit about the MOSAiC distributed network of buoys, of autonomous installations, and a bit of an overview of ocean activities, ocean here meaning mainly physical measurements. Yeah, Matt already gave you a pretty good impression of what we faced when we were out there, and it was an amazing time, but also a very challenging time. And here you see 2 interesting pictures. The left-hand one is actually from the first leg where Matt was on as well. The second one is from the leg I was on, and it got a bit colder. It was equally dark as at the end of the first leg. On the bottom left, you see a Russian ship that helped us really to distribute, to deploy the distributed network of buoys in the beginning. That was also an amazing feat. So a lot of people working together very well. Yeah, I really like this figure of Matt. I know it's a bit complicated for the non-scientists, but actually it just illustrates to you all the sorts of processes that we actually want to study. So there's so much going on when you go up to the, you go from the atmosphere all the way through the ice into the ocean. Sometimes there isn't ice, and that also makes it very interesting. So you have leads, and suddenly the ocean, before I was shielded from the atmosphere by the ice, suddenly is open. Before refreezing, and also even after, there's a lot of exchange through there, anything from gases to energy. So I think this is really a whole multitude of things we were going to look at. And I'm going to focus here in the ocean part on that part. Obviously, when I talk about the distributed network of buoys, I will also talk about other buoys. So basically, the general concept, I think, was already introduced by Matt. So you have a central observatory, but around that, you have other ice flows, right? So we were in the middle of the Arctic. There was ice more or less everywhere. It was actually a challenge to find good ice flows, not only one ice flow for the central observatory, but also for all the different buoys, because some of these installations are not that light. They can be up to several hundred kilograms. So you don't want to put them on very thin ice, which starts to reach raft, and that thing just kind of gets crushed in between, even if it has some buoyancy to float up. So those are the kinds of things you see around here, those little things here on the ice flows around the central observatory. Once that was all deployed, thanks to Leg 1 and Leg 1, the beginning of Leg 1 with 2 ships, and at the end of Leg 1, we could actually join and have a fully installed and relatively stable central observatory. When we were out there, though, in the middle of winter, the distributed network did still show a lot of dynamics, and some of our buoys got a bit crushed, and I'll tell you about that later. You see the drift on the right, and basically, I'm going to show you a few pictures. One was right from the second leg where I was one, which is the bit in yellow here that Matt was talking about. And the others are actually from the end of Leg 3 down here, the same installation. Here you see on the top left, there's one of the main things that happened related to the ocean next to the ship. There was a hole, and a device went in there that measured a lot of different things, among others, temperature, salinity, and pressure, had sensors for all sorts of other things like oxygen. And most importantly, you could take samples by different bottles on there. It's here actually hidden under that red thing there. And it was a great achievement of the first leg to make that work, because if we hadn't been able to put it that far away from the ship, next to the ship, the ice is actually piled up. So literally the same as ice rafts and ridges, you would get a ridging next to the hull of the ship. So below there, the ice can be several meters thick. Whereas in that hole here, it was something like 2 meters, I think, at the end of the second leg when we were there. At the bottom left, you see the second really important installation for the physical oceanographers, and also for some of the eco and biogeochemical sampling people. And you can see here on the map on the right, I suppose Matt already showed you a map of one of the different configurations that we were working with. Well, here you can see Polarstern is marked by the yellow cross on the right here. And on the left, there is another yellow cross that's about 300 or 400 meters away. That was the actual distance on the ice floe. And that's what we called Ocean City. And just like Med City, it was another remote outpost where we could actually do our measurements. The advantage we had there, we were not disturbed by the ship, but we were also independent of that ice hole next to the ship. So we had the same kind of device in there, plus various other devices. So here in the background, you see that device that is actually put over the side of the ship, that is here hidden under the red. The same kind of device, in a bit smaller, existed in that tent. And the tent was actually on pontoons, so it was a bit more protected. And yeah, we could measure there in the nice and warm. So the only main problem was getting there. And of course, conditions outside had to be sufficient for a Bergard to operate. But otherwise, it was a very nice haven to do our measurements. So these are just 2 members of leg 3 that came at the end of our Leg 2 to take over. Unfortunately, things didn't always go right. So at the top left, you can see we lost the CTD hole near the ship during Leg 3. And this was when the ship was moved by motion in the ice, and the gangway actually crushed that tent here that was protecting the hole from freezing over. Later on, there was a crack that went right through the middle of that hole, and the hole was gone for most of Leg 3. Ocean City actually also had trouble. So Matthew already showed that one of the ridges was approaching next to a previous crack in the ice. Well, they had to be relocated a bit. Here you see challenges during the third leg where the power lines were severed. So they had to actually set up a generator on the sledge that would supply the tent with power to run all the devices, and a fuel barrel here right next to it, which had to be replaced regularly. Apart from field work, we did we have some great results in our measurements. Here you see one result that's already been published. This was measured by various devices. Here is a device that, oops, sorry. Yeah. Here is a device that measured temperature continuously. And in this particular case, it's a departure from freezing. So where you see the blues, the temperature is actually close to freezing or even sometimes slightly below it. The reason why the person who's actually a sea ice physicist was prompted to do this analysis was by these kind of platelet ice that you can see in the pictures on the bottom left here that started to form in these conditions. And we assume that this had something to do with the fact that the water was even sometimes below the freezing point. And here on the middle, you can see a few lines. These are vertical profiles. So on the left, you see the depth, and then the bottom in the x-axis, you see each of the values. On the left, you see salinity, which pretty much shows you the upper mixed part of the water column, which is here about 40 meters deep. And then the salinity started to increase. If you go all the way to the right, this is again the departure from freezing. So the difference in temperature from the freezing point, and it's negative in the upper part of that mixed layer. The reason why it's not negative below, even though the temperature is fairly constant, is partly to do with the fact that the pressure increased. And these conditions we think probably led to the deformation of this platelet ice, but this whole super cooling, as we call it, is still subject to further research after the cruise, when all the sensors have been post-cruise calibrated and so on. Another interesting thing is you can look at this mixed layer depth. So this upper part of the ocean that is mixed and it is in direct contact with the atmosphere and the ice. You can look at the depth throughout the time. And that's what my colleague from the third leg, Janine Schaffer, did. And she actually plotted here that mixed layer depth. And as you go from early winter, where of course the mixed layer depth is still not that deep because it's still from summer where you have a lot of melting, so the water is re-stratified, you get a shallower mixed layer. And throughout winter, this mixed layer gradually increased. Here on the right, you can see it on the map. The map shows you in color the mixed layer depth. So the kind of yellows and light greens are shallow, which was still happening on the first leg. And then throughout the second, and in particular the third leg, the mixed layer depth got quite a lot deeper. And we obviously still need to figure out how much of that is just the spatial variability, because we went through different basins, different conditions in the water, or what is actually seasonal. Now I'm going to talk a bit about the distributed network. So this distributed network buoys was really a challenge to put out. So our original plan had been to put all these green spots, which are kind of medium-sized buoys that may weigh kind of 100 kilos overall, or 60, 70 kilos, to put them much closer to the red star, which is Polarstern. In the end, the people who deployed the network did an amazing job in deploying pretty much all of it, some of it a bit further away because they couldn't find suitable ice close to this Polarstern, because if it's too thin, you don't know if is there some more rafting going on at the beginning of the freezing season, and then you may lose your buoys. Those blue ones here are heavier buoys, so they're those kind of installations where Matthew already showed that atmospheric buoy that was on the sled. Those were at these 3 points, and other heavy equipment for ice and ocean measurements. And the little triangles are just position buoys, so they literally just track the motion of the ice. So you can get a bit more data to track that different rafting, ridging, and moving around. Here you see a few pictures. So on the left, there are two colleagues of mine, Ying-Chi Fang and Mario Hoppmann from ABI, who actually deployed one of the medium-sized buoys. And on the right, you can see people deploying a snow buoy. At the top right, you see they actually have it still lying there. They're drilling a little hole. The buoy actually more or less sits on top of the ice, but it needs a bit of something sticking into the ice to just have a bit of a hold, and also to keep the batteries a bit less cold. So at the bottom, you see this is the kind of buoy that has a top buoy, and then they have several sensors, as you can see in green here underneath at fixed depths. Whereas on the right, the buoy is literally just sitting on top. So that's more similar to the buoy that Matthew showed earlier, only this one is observing the snow thickness, whereas his was observing fluxes in the vertical next to the surface. So I'll give you a bit more of an impression of this leg 2, just because I was there. We were in middle of winter. We were very far north, so this is like early February kind of time. And you could see it was pitch dark. The only time it was actually a bit lighter was when the moon was out, and that was amazing because we could really use that light. And if you took pictures long enough, with long enough exposure, you would actually, it would look like sunshine. But it was an interesting time. We were 750 kilometers away from the next human, so it was an amazing time. Here you see again a few pictures of this distributed network of buoys. So just to give you an impression what these things look like in midwinter. Obviously they got snowy. Here on the left you see a Woods Hole ITP. This is a profiler that profiles the top part of the water column, so measures temperature and salinity. Then here you see a flux buoy, the same kind of thing that Matthew showed, which you see on the right here a picture of, but measuring that kind of thing right under the ice. So taking the fluxes from the other side of the ice, if you like. On the bottom left here, you see a radiation station and a mass balance buoy. On the right here, you see another type of buoy. The surface buoys all had very different shapes, and some just measure simple parameters like atmospheric pressure and temperature. So that's just to give you an impression what it looked like in winter. That was still fine. On the right here, you can see, unfortunately, things weren't always fine. So even though our central observatory in Leg 2 kept kind of in the middle of winter fairly stable, around us, a lot of dynamics were happening. And here we can see what happened to that nice flux buoy of Matthew. It got completely overturned. But they actually rescued pretty much all of that and redeployed it. On the top, you can see a picture from the other side. So Matthew already showed you a picture from the behind this atmospheric buoy. Now I show you from the other side. There's the ocean flux buoy and the wind generator. I think that was never seen again after the ice moved a bit more. Here you can see what happened when we recovered the network after the instruments collected all that really great data that we can work with. It did an amazing job in addition to all the manual measurements we did. And this was time of meltdown, right in August. So the ice tether profiler from Woods Hole here, just floating, kind of still standing on a bit of ice, that was recovered. The the ocean flux buoy was recovered. That here is the atmospheric flux buoy that Matthew showed, that was recovered. There's a snow buoy here. So they recovered several of those buoys as much as they could when it was in the Farm Strait where Matthew showed the end of Leg 4. And the good thing there was the ice was melted so much that it was actually much easier to retrieve those buoys than it would have been if we would have tried that during heavy ice conditions. Here I can just show you a brief glimpse of a bit of data. Don't worry about the details. All I want to show you is some of these fixed layer buoys where we had, so let's say at 10, 20, 50, 75, and 100 meters, we had measurements of temperature and salinity. You can get amazing time series out of these. So normally on the ship, we would do these kind of measurements, once a day with a profiling device of some sort or several times a day. But this gives you continuous time series at several minute resolution. So you can look at all sorts of interesting things. If there was a storm, what happened to the temperature or salinity at that depth? Did it get water mixed down? Did the stratification, let's say the stableness of the water column change? On the right, you can see an autonomous profiling device similar to the Woods Hole ITP. This is from Chinese colleagues. They had one that profiled a bit shallower, did that twice a day. And you can see the development of salinity throughout the year. And in fact, this is at the bottom here, you can see this sharp gradient in salinity gives you some idea of the mixed layer depth. And that's what I already showed earlier, that it kind of deepened. What you can also see here, that this is just one buoy, right? Each is just one buoy. Well, we had several of those, as I showed you earlier, and they were in a network around us. So if you plot the track of Polarstern, these are all the wiggly lines of positions that you get if you plot all the buoys as well. So it was an amazing amount of measurements that we had in addition to what we did at the Central Observatory. All sensor based, of course, so no samples could be taken by these devices, but they did some really cool measurements. And I can see on the left, don't worry about the actual variable. This variable just shows you the expansion of the water column due to differences in temperature and salinity. But what some of our people have already started doing is taking these wiggly lines of measurements. This is a sort of an integrated thing over the part of the water column, and put it on a regular grid. And that can then be used in models to say, give them the initial kick and say, this is where you start to model and simulate what we want to see. And they can then simulate into the future and give you a better idea of what's happened spatially, because our measurements, of course, couldn't resolve everything. So those are the really great things we can do with this data. Another important thing that was done was measure the turbulence in the water column. So how strongly is everything mixed on a very, very small scale. So the little whirly bits that mix up the water column, a bit like if you steer with a spoon through your tea, the sugar will mix up quicker, that kind of thing, than if you just leave the sugar at the bottom. And at the top, you can see, yeah, we did these measurements inside this Ocean City tent. During winter, we had this tent pontoon setup. Here you see kind of a series of when I take some measurements. Later on, in the following lakes, they had to use all sorts of ingenious ways to measure. Here on Lake 4, they were measuring in the lead, so the system is fairly mobile. You have to get out there with a sledge. Sometimes they were not able to use skidoos, so they had to pull the whole thing. Here, there is this tent that Matthew already showed, where one of our colleagues is doing these measurements. And here on the right, full day in the fog, those are of course the challenges you face even if you have daylight. So I want to finish now, and thank you very much. And all these people who really participated a lot. So of course, there's my co-coordinator, Celine Uzé, but there are various people who were the leaders on the different legs for Team Ocean. And there were so many people on board. Most of these people actually participated in the expedition and did great measurements. Quite a few, though, did also do great work at home to support the whole affair. So really, thank you very much. And look out for presentations if you're attending any scientific conferences. There's AGU Fall Meeting coming up. And then there's the Arctic Frontiers in January and the European Geophysical Union in April. So thank you very much.
Thank you, Ben. So I have just opened the chat up again, so you should be able to chat your questions in there. So if you have questions for Ben or Matthew, please go ahead and either put them in the chat or you can use the raise hand function and I'll let you know that you can go ahead and unmute. So Matthew, I think this may be a good question for you. Sasha Liedman is asking about the sexist dress codes and policies on the academic federal. It's not the Polarstern, but MOSAIC needs to address the environment of discrimination throughout its scientific expeditions. What is the Polarstern doing to make sure that sexist policies such as this do not happen, and that the experiences and hardships of female and minority researchers are recognized?
Yeah, I mean, this is a great question, and it's one that we struggle with all the time. I mean, I would say that the issues raised in those articles are not a MOSAIC issue, they're an all of us issue, right? They're an issue that cuts across science, and it's one that we need to come to terms with. And, you know, the events that happened related to MOSAIC were unfortunate at some level. They were a conflict of cultures and some challenge with communication. That's about the extent that I can go into that. I can say though for sure that we did implement policies within MOSAIC that provided a safe space for people to express themselves. We definitely had policies in place as far as the behavior and interaction between the different individuals that were participating. And also importantly, I want to point to some of the successes. You know, those successes were not put forward in those articles, but, you know, as the article came out, the first one, I was just coming back from leg 4 where we had pretty much 50-50 in terms of male females on board, and of the 10 people on the leadership team, 7 were female. So to me, I'm not saying that MOSAIC was perfect here, but I'm saying there were successes that we had in the field that are worth also highlighting. And it's something that, you know, hopefully we as a scientific community can continue to make progress towards improving our gender balance in the field and our treatment, kind of equal treatment of all genders.
Thank you, Matthew, and thank you, Sasha, for your question. Again, if you've got questions, you can put them in the chat. You can also use the raise hand function. We've got a question from Stephen Petras asking, what is the makeup of the water in the melt pools, and is there any life in them?
Shall I answer? I mean, yes, there is life in them. All sorts of strange things. I remember on one expedition I was there and they looked like little pieces of bread. So obviously there is life in there that you can probably compare to plants on land. And there's life on there that you could probably compare to small animals on land, the kind of stuff that Matthew has shown, which is usually more in the water column, but you can find similar creatures in there. That's as far as the extent as I can tell you about biology. Maybe Matt got a bit more. What is interesting though, they do have very different salt content. So the salinity of those melt ponds is not always the same, or mostly not the same as in the water below. So you can get a lot lower salinity, so almost fresh water. You can get water that's very salty. Once I remember one piece of my equipment went into one of those melt ponds and it was unfortunately just a melt pond that was very salty, so I wasn't very lucky. But yes, so that's it. And what happens at some point is that they melt through. So in summer at some point, it melts so much from the top and sometimes from the bottom that the melt ponds actually break through, and then the water is often drained because the ice has a certain freeboard, so it floats a little bit up above the surface of the water, and then suddenly things change. So those kinds of processes really obviously influence the biology in those melt ponds as well. I don't know, Matthew, if you have anything else that you heard, but I think
sounds good.
We've got a question to see the slide again about the 20 countries cooperating, 7 icebreakers. Matt, I think that was your slide.
Sure. Let's see. We can see that again. I don't know if there's a question about it.
Just a request to see it. Anna, do you have a question about it?
I will emphasize that there were many more nations involved through the people. And I was actually super impressed by the number and different types of people that were there and the way in which everybody worked together. It was just truly amazing, the volunteerism and the cooperation that happened in order to implement all this science. And, you know, it really didn't matter what your native language was. It really mattered, like we all spoke a common language there. The language of science, and so that was really tremendous to see all this kind of international cooperation.
Great. And it looks like there wasn't a specific question, just wanted to see it for longer. So thanks for pulling that up again, Matthew.
Yep.
And then a question came in from Michael Duxbury about what impact, if any, was observed that the Polarstern had on the ice it was studying.
Yeah, well, so a lot of the observations were designed in a way to try to minimize that impact, right? We're not there to measure the impacts of a ship, we're there to measure a natural environment. So therefore we had the distributed network, we had all these little ice stations and camps and cities out on the ice to try to get away from that. Of course, the ship itself, you know, I'm an atmospheric scientist, and the ship has exhaust, and that affects the aerosol composition that can put out black carbon, that can affect the albedo at the surface. We had people measuring those kinds of things. So that's one of the impacts that we certainly could see. Another is that, you know, the ship releases gray water, for example, as part of its typical patterns. And there again, we don't want to measure that in the ocean. And so we tried various means to try to recognize that. And so we could eliminate that. And that goes down to different timing of when we make samples. There was some tracers that were put in, things like that. So we really tried to identify and minimize the impact of the ship itself on our measurements.
Thank you.
Perhaps I can quickly add that we also we chose specific measurements to be done just away from the ship because we knew they would be influenced by the ship, whereas with other measurements, we knew that it was okay, so we did them there. So I can tell you, for example, ocean turbulence, if you want to see the mixing and turbulence in the upper water column, obviously you don't measure right next to the ship, right? If you want to see the upper 20 meters. But if you want to do other measurements that capture a larger depth range and aren't so affected by that, then you can do them near the ship.
Candice Nachman, I saw you had raised your hand. Do you have a question?
Yes, and I typed it into the chat because I do have to leave in a couple of minutes. But I want to say I was really pleased that you guys were able to add a fish study to the scientific plan of MOSAiC that I know took place, I think, on leg 2 maybe. And I didn't know if there were any preliminary results from that work that you guys could talk about.
I would say that I'm not going to talk about them, but there are results. And actually the fish study was ongoing over the whole time period. And I believe that you should be able to find those results in nature before too long. So pretty exciting there.
I was hoping you guys would spill the beans. I keep getting told to wait. All right, thank you.
All right, I think we have time for one more question, and I see Jack Zib has asked a question in the chat asking about the period of rapid drift in leg 3 and whether it was mostly anomalous winds or if it was ocean currents or if it was too early to tell.
Well, Ben, I don't know about the ocean currents, but I do know about the atmosphere, and the atmosphere was anomalous. I mean, I showed that plot of anomalous winds. The pattern was very stagnant in the atmosphere. And so whereas you would typically expect the path to be kind of meandering, it was actually very straight. It just sent the whole drifting constellation of observations along the transpolar drift very quickly. And so we know for sure that the atmosphere was anomalous. I'm not sure about the ocean component of that or how those two interacted to really to give us the result that we had. But yeah, the atmosphere definitely played a role.
Yeah, I think I want to second that. So what you said, Matthew, is really the point, the interaction. So I think in years where you have this really anomalous drift in the transpolar drift, that obviously there is a strong atmospheric driver there. I would say that intuitively. But there can be feedback with the ocean, and that has been observed in other parts of the Arctic where sometimes actually the ocean circulation reacted to the ice speeding up or slowing down and then affecting the ice motion as well. So the wind is not just pushing the ice, the ocean can also push or even slow down the ice. So, so I think that's still research to be done actually.
Oh, sorry, I see Jack says high winds and stagnant don't go together. By stagnant, I mean the large scale circulation pattern was relatively stationary. So I don't mean stagnant in terms of the winds themselves. I just mean the pattern was not changing very much. And so it stayed in the same direction for a long period of time.
All right, so we are at the top of the hour. So I do feel that we should cut off, but I do see one last question that maybe we can take real quick. About whether how Indigenous knowledge holders have been included in the planning and execution of the expedition. Matthew, I don't know if you want to speak to that before we wrap up.
Yeah, I would say that this is definitely an area of weakness for MOSAiC. We did not have a lot of Indigenous knowledge holder involvement in general. There certainly was some via the whole interaction with IASC. There's of course a whole community of people from the Indigenous community associated with IASC. But we did not have anybody specifically core to the MOSAiC science or research. Part of that was a decision just about the stakeholders in the Central Arctic and the fact that people don't live in the Central Arctic out over the sea ice. We tried to place some boundaries on what the bounds of the science would look like out there. And that was one of the decisions that was made at some point about engagement for the local communities.
Thank you. So again, thank you to our presenters. I really want to thank both Matthew and Ben for taking the time to present. I also want to thank John Griffith and the entire series team for MOSAiC who helped put this together and have helped put our entire MOSAiC Month events together. And I am putting in the chat right now a link to our MOSAiC Month page on IARPC Collaborations, where you can see all of the events, including the ones coming up on October 19th, which will be both a series of lightning talks by early career researchers who are out on MOSAiC and a joint collaboration team, which actually Matthew will be back at. So again, thank you to our speakers and to John for helping organize, and thank you to all of you for joining us.